Okay, and so getting to this week's and today's lecture. So from our usual roadmap, over the last few weeks, we started looking at kind of modern ways to approach learning-based control. We started from imitation learning, where the idea there was to learn to mimic the behavior of an expert. And then last week, we started to introduce reinforcement learning, which is this idea of learning through trial and error. And specifically, we introduced some foundational learning mechanisms to do so. And starting today, and for the next lectures, for the remaining lectures of this class, we'll be looking at specific categories of algorithms. Today, starting from value-based methods that belong to the category of model-free reinforcement learning methods. Briefly mention a couple of amazing references. Of course, you all know kind of probably Sutton and Bartow's textbooks on reinforcement learning, but also this course by David Silver, which is great, and also some of the slides today are indeed inspired by that course. So to briefly pick up what we were saying last week. So remember that in previous lectures, we basically started to make the distinction between what we refer to as prediction, whereby given a policy that was given to us, we wanted to estimate the value for the policy, and control, whereby the goal, which is actually what we deeply care about, is to learn the policy that optimizes some measure of performance. And specifically, we started looking at algorithms motivated by dynamic programming, which we refer to as exact methods, specifically policy iteration and value iterations, as ways to solve Markov decision processes, which is indeed the mathematical formalism we are using also for reinforcement learning. And we also highlighted how these models, despite being great at solving Markov decision processes, had one main limitation, which is the one that in order to use them, we assumed we have a perfect knowledge of the system dynamics. Specifically, we have knowledge of the transition function T, which is the probability of going in state xt plus 1 given in state xt given action ut. And so, basically, last week, we started to introduce two really fundamental learning paradigms which really encompass this idea of reinforcement learning, which is learning from interaction, right? So we don't have access to a dynamical model. We want to learn without it through interactions from the environment. And we saw specifically Monte Carlo learning and temporal difference learning as two key instantiations of these learning paradigms. We started building out, even visually, kind of a mental map of different approaches to learning from interaction, whereby we were looking at these diagrams, which essentially represent rollouts in our environments. So if you recall, in these diagrams, white nodes represent states, and black nodes represent possible actions that we could take in that specific state. And so these basically kind of visualize this idea of the possible futures that we could have in our environment. And ideally, when we look at estimating the value of a state given a policy, we are ultimately interested in estimating the expected value over all the leaves in our possible rollouts, right? So this is the actual quantity that we're interested in estimating. Of course, kind of one way, assuming we have infinite compute, would be to just simulate our environment infinitely many times forward, collect the actual expectations of all of our leaf nodes, and estimate the values like this. But then we saw how dynamic programming gave us, through the principle of optimality, gave us a practical way of approximating and calculating actually these values through basically a one-step calculation, whereby the value of a given state was essentially defined as the expectation of the reward that we observe in the one-step transition plus the discounted future value at our next state. The catch here is that to compute those expectations exactly, we needed the knowledge of the transition function or our dynamics. And so this is where Monte Carlo and temporal difference learning came in place, whereby we used sampling, that is, we simulated some rollouts in our environments. And in Monte Carlo, we update our guess of our value function by taking a step in the direction of the return, GT, where we calculate this GT simply by having a rollout in our environment until we reach a terminal state and summing up all of the rewards that we observed in this rollout. In TD, on the other hand, we define the target by basically leveraging ideas from both Monte Carlo, that is the sampling, and dynamic programming, that is the bootstrapping, by defining the target as this one-step estimate of the final return. And so we saw how, compared to dynamic programming, which has no need to sample because we have the underlying dynamics, Monte Carlo and temporal difference learning both sample because we do have interactions in our environment. And we saw how TD and dynamic programming bootstrap because they update the guess towards another guess, which is our estimate at the next time step, t+1. While Monte Carlo does not bootstrap because it actually rolls out until the end of the episode. Of course, we introduced everything in this slide for the purpose of estimating value functions or state value functions V, but everything that we just said holds equally for state action value functions or Q functions. For control, yes?
For Monte Carlo, does it always have to go to a terminal state, or like, is there any where you go and you take like 5 steps and then reevaluate it?
For Monte Carlo, you always need to reach a terminal state. Which is indeed, if you wish, one of the limitations of Monte Carlo. But we discussed trade-offs between bias and variance of these estimators. But yeah. But so this is great for the purpose of prediction, that is estimating values given a policy. But what we actually care about is finding those optimal policies themselves, right? So we care about control. And so we discussed kind of a general paradigm for control, which is the one of generalized policy iteration, whereby the main idea here is that we are alternating between two different processes. So we're given arbitrarily initialized value function and a policy, and we alternate between a policy evaluation step, that is, given the policy, we estimate the value function of that policy, and a policy improvement step, which given the updated value function, kind of uses it to carve out a better policy out of it. And by iterating through these two processes, we hopefully converge to the optimal value function and associated policy. Specifically, we saw kind of a V0 version of a working control algorithm, which we refer to as Monte Carlo control, which is basically alternating between two specific instantiations of the policy evaluation process and the policy improvement process. For policy evaluation, we are essentially using a Monte Carlo estimate of a Q function. While for policy improvement, we assume to do an epsilon greedy policy, if you recall. So again, we saw this general formalism, and then we had like a V0 RL algorithm, which we denoted as Monte Carlo control, where we had two specific instantiations of policy evaluation and policy improvement. Okay, so today, what we'll essentially be doing is we'll be building on top of these concepts by, first of all, introducing two very popular algorithms like falling between the family of value-based methods, which is SARSA and Q-learning. We'll use the discussion on these two algorithms to deep dive and explore a bit more in depth the difference between on-policy and off-policy algorithms. We'll see more shortly. And then we'll introduce value function approximation as a way to scale these algorithms to higher dimensional state and action spaces. And we'll conclude with brief mentions to some deep reinforcement learning methods and applications. All good with the plan? Nice. Okay, so we basically discussed Monte Carlo and TD learning, and last week we mentioned how temporal difference learning essentially has, if you wish, several advantages over Monte Carlo learning to some extent. The first one is that we saw how TD learning is a lower variance estimate of the ground truth return. So remember that we were making this even visual distinction, whereby assuming we have a rollout in our environment until we reach some terminal state at time t. In Monte Carlo, to estimate the expected return for our policy, we would essentially be rolling out the entire episode until we estimate, until we're able to compute our target return GT, which is simply the discounted sum of all the rewards that we observed over time. And we saw how this target, which in Monte Carlo is simply the return, for TD, we basically used the kind of a dynamic programming estimate, whereby our target becomes the instantaneous reward plus the discounted future value. And last time we basically highlighted the fact that by looking at the amount of stochasticity that is involved, TD learning is a lower variance estimator because simply put, we're sampling only once, while in Monte Carlo, in order to estimate all the way down here in our episode, we would have to account for the added stochasticity that comes by sampling in our environment for further along the way, essentially. Not only that, we also discussed that since in TD learning we are working with one-step updates, we can use this update online. That is, as we progress in our rollout, we could keep updating our estimates of the value function. And because we don't need a terminal episode, we can work with incomplete sequences, essentially. So, long story short, we have a number of advantages from TD learning. So kind of a natural idea would be, why don't we just replace in our Monte Carlo control algorithm, that is our V0 RL algorithm, TD learning where we previously had Monte Carlo learning of our Q function. And basically, this is essentially the step that leads us from our Monte Carlo control algorithm to what is known as SARSA. So let us look a little bit more closely at what it means to update action value functions or Q functions within this algorithm known as SARSA. So specifically, we referred before to the temporal difference backup as updating our guess of our value function by taking a step towards the TD target. Of course, this holds for value functions V, but equally for Q functions in the same way. Of course, the moment we want to define this TD backup for Q functions, we need a few specific elements, right? Which are essentially we need the current states and control, xt and ut. We need the reward that are obtained from those by taking that control in that state. And then we need the future state xt and the future control that we take at t+1. But once we have this is essentially what defines the Q function update in this algorithm. So specifically, now just a note on notation, in reinforcement learning literature, this quintuple of events is usually expressed with states represented as S and actions represented as A. And so if you take this quintuple of events, which are the ones that we need in order to define this update, this literally spells out SARSA. And so this is also where the name of the algorithm comes from. But again, kind of simply put, at a high level, what we're doing is that now we took our Monte Carlo control algorithm, we replaced Monte Carlo evaluation of the Q function with TD updates of the Q function, and we're doing this at every time step, because this is something that TD allows us to do. And so indeed, you see that the step from what we're doing to arguably one of the most famous algorithms out there, SARSA, is indeed pretty small, right? And so I think it's useful to go through pseudocode to really ground our intuition. And so this is, if you wish, how SARSA is loosely defined. So we initialize a Q function. Again, this could be all zeros at the beginning. And we start our learning loop. So we are initially initialized in our environment at some state xt. At that state xt, we choose an action according to our greedy policy, or epsilon greedy policy. So remember that we discussed how our policy pi, if we choose an epsilon greedy policy, is something that with probability epsilon, we'll choose a random action. And with probability 1 minus epsilon, we'll instead choose the argmax over u of our Q function. So we are in a given state. We act according to our epsilon greedy policy and pick an action U. This will lead us into, will basically give us a reward for that action, a next state, from which we repeat kind of the selection of our control, ut plus 1, according to our epsilon greedy policy. And now we basically collected all of our 5 elements that we need for our update, right? So we have the initial state and control, xt ut. We have the reward associated with this control, and the following xt plus 1, ut plus 1. And so here we just simply compute this update rule that we defined previously, which is nothing else than the TD backup for Q functions. Of course, here the clock ticks, and we kind of repeat until we converge. Any questions here? Does it make sense? Yes. Yes, indeed. So here we're using kind of a TD version of our update for the Q functions, where we are updating our value functions according to the basically one step look ahead, you might say, right? So we're taking one step in our environment, and as we were showing here in our pictorial diagrams, we're essentially using only this one step update to update our values. Okay. Okay, so let's dig a little bit deeper and let's build some intuition into what we're actually doing here and what are the results from the perspective of the policy that we actually learned. And so let's go through this, what I'm referring here as a windy grid world example. So here we are in a grid world where the goal is, as usual, to go from a starting cell to a goal cell G. The policy, or the action space, is basically the 4 cardinal directions. And in this grid world, kind of the catch is that we assume we have some kind of fictitious wind that is coming from below, which basically pushes the agent X cells up, depending where X is the value encoded here below each of these columns. So for example, if we were in this column here, in the third one, we would have no wind. If we were in the fourth, we will be pushed 1 up, and so forth. As usual, the goal that we want to solve is to basically come up with the policy that reaches the goal in the minimal time possible, and we encode minimum time through a stage-wise reward that is -1 for each tick every time our clock ticks, essentially. And we have some specific hyperparameters. Epsilon refers to our epsilon greedy policy. Alpha is the step size of our update, and we pick a gamma of 1. Okay, so now, even just by eyeballing this example, how would you describe the optimal policy here?
In the bottom part of the thing before you move to the right.
This is a good intuition. It's actually not correct in this case. Can anyone spot why? Yeah.
You can't move over and up in the same grid, so you go all the way to the bottom. It's going to push you over G by the time you get there.
Yeah, exactly. Because if you look closely at the kind of the intensity of the wind over here, if you're way all the way to the bottom here, you'll basically go up here, then you take 1 step and you go up again. You take 1 step and you go up again, and then here we're taking 2 steps, right? So you won't be able to reach. So actually, it turns out that the optimal thing to do will be to just push yourself to the ceiling, and then go back. And so here, go back here, and then ultimately go to your goal. So here, here's where I ask you to do a leap of faith. But if you actually implement this in practice, what you will see is something that looks very similar to what is here on the slide, whereby first of all, SARSA indeed does converge to the optimal policy, which is similar to how we described it. And by looking at the training dynamics, we will see something similar to this plot on the slide. Specifically, this plot is showing on the x-axis the time steps of interactions with the environment. So literally how many time steps we are observing in our environment. And on the y-axis, we have the number of successful episodes, meaning how many times do we actually reach the goal. So you will see that initially our Q function is, and therefore our policy, is randomly initialized. So we'll basically be succeeding 0 times, so we never reach the goal. Until at some point, even just by random exploration, we will reach the goal. And here's where kind of the magic of the TD backups start to happen, because through those backups, we're basically starting to backpropagate the basically positivity and the goodness of our decisions all the way back to the starting point. And so you will see that over time, kind of the performance of the policy improves. Do the graphs here make sense? Now, would you say that, within this environment, would you say that Monte Carlo methods would also easily apply? And in either case, why do you think so? This is kind of a more subtle question, but I think it's a good one to think about. Yes?
It wouldn't be the case because you would try out a bunch of different combinations and you only terminate it once you reach your goal. And so as a result of that, you spend a lot of downtime just having it kind of wander around until eventually it lands on the goal.
Yeah. I would say this is definitely the right intuition. Because in Monte Carlo methods, remember, we require terminating episodes. Well, in this case, terminating episodes is only when we reach the goal, right? So we might be lucky in the sense that we end up into some random exploration that does reach the goal. But in the general case, it is not guaranteed that we'll be able to do so, right? So I think like a nice counterexample to think about is say that in our grid world example, we have a situation whereby for some behavior of our learning dynamics, we converge to a temporary policy that is something like this, right? Something where we have kind of a circular loop in our policy. Then in Monte Carlo, this will essentially never update the Q function, and it will be stuck in this loop. On the other hand, if we are in the same situation with TD learning allows us to update online, right? So at each step, we are actually updating the values in our Q function. And so this means that if we were to be stuck in these circular loops, at some point, we are basically accruing negative rewards over time. And so this would mean that these specific behaviors at some point will be actually worse than doing something else. Indeed, and so it's exactly as we said, in the sense that termination is not guaranteed for all policies here, and therefore kind of success of MC Monte Carlo learning is not guaranteed as well. Okay, so we now introduce, if you wish, one of the one of the first complete reinforcement learning algorithms, namely SARSA. Let's use SARSA as a kind of grounding algorithm to start discussing the differences between on-policy and off-policy learning. So we mentioned it briefly before, but let us briefly revisit also the definitions of what we mean by on-policy and off-policy learning. We'll dig more later on this, but this is kind of at high level how I would describe on-policy and off-policy learning. So for on-policy, we mean that we are interested in evaluating or improving the policy that is currently used to make decisions in the environment. On the other hand, for off-policy, we are interested in evaluating or improving a policy that might be different from the one that is used to generate data, that is, the one that is actively interacting with the environment. Again, we'll formalize this a little bit shortly, but I think this is intuitively kind of the main difference. Now, with these two kind of loose definitions, in which of these two buckets would you place SARSA? And again here, why would you do that?
it's also the off policy because you're
So we are modifying it, but I would argue that we are modifying the policy that is actively being used in the environment, right? So I'm kind of giving away the answer a little bit, but in this case, and in general, SARSA is to be considered an on-policy algorithm. Because if you look at the pseudocode a little bit more closely, we are defining our policy as the epsilon greedy policy. And we are indeed improving this same epsilon greedy policy, right? So the policy will change over time, and you're correct. But we are indeed gonna be improving the same policy that is being used to interact with the environment. So yeah, SARSA is indeed an on-policy algorithm. But so let us now dig a little bit deeper into off-policy learning. How do we define it slightly more formally? And also, why do we ultimately care about off-policy learning? So in general, off-policy learning is can be seen as the mechanism through which we want to evaluate a target policy pi. That is, we want to compute the associated value functions for this target policy pi while following a behavior policy mu that is a different policy. Specifically, the data we'll use to define our update equations will basically be sampled by interactions in the environment that are collected by following the behavior policy mu. Right? So the data here is obtained by observing a different policy. So why would being able to do something like this be useful? So first of all, in some cases, for example, robotics to be one, we might not have the luxury of actually interact with the real world or with the environment infinitely many times, right? Maybe in some cases we can only learn through either observations of humans or other agents doing things, and therefore kind of having this framework whereby we are able to evaluate and learn about a different policy from the one that is the one that generated the observations is actually a nice thing to have. Kind of a second reason is that so far, so remember our generalized policy iteration scheme? We described these alternating processes where we are gradually improving our policy over time, right? And so if you see this now a little bit more holistically, in the environment, we are generating data according to changing and hopefully sequentially improving policies, versions of the same policy, right? And so far, we're basically saying that we have some interactions with the environment, and we only use the most recent versions of those interactions to update our values, right? So all of the previous data that was generated from the previous versions of my policies, we were basically throwing it away, right? And so I hope it's, it's pretty evident that this might be wasteful, right? So maybe there is some information to be gained from previous data. And lastly, so this is slightly more subtle point, but also I think the reason why off-policy methods are also best known for. And it is because by decoupling, if you wish, the behavior policy from the target policy, we're essentially able to posit the problem where we want to learn about the optimal policy that is likely to be, an exploiting policy, typically deterministic, from the exploratory policy, which is the one that is maybe a little bit more random and free of exploring our environment. But so I think these are all great reasons for which off-policy learning is actually very important. So now let's look back at what we were doing for SARSA, where we were basically updating our Q functions in an on-policy way. And let's see how we could modify what we were doing in SARSA in order to basically follow this off-policy paradigm. So remember that in SARSA we were using behavior policy, mu. So here we're already using the new notation to generate our quintuple of events, right? Specifically the state and control at time t, the reward, and the next state. And then we're also using it to generate the next control. However, now let's consider an alternative successor action, u t plus 1 prime, which is generated from our target policy, right? If we were to use now this quintuple of events in defining the update, this would essentially represent a way in which we are updating our Q function Q towards the value of the alternative action, right? So if you look a little bit more closely at what we're saying here, is that we're updating our Q function for xt ut by taking a step in the direction of the TD target defined by the value of the alternate action u, ut prime, t plus 1 prime. Right? Now, basically the formalization of this, so how do we if we want to now instantiate this idea into a working algorithm, this would directly lead us into defining Q-learning, right? So specifically in Q-learning, we would define the target policy pi as the greedy policy with respect to Q. Again, the target policy is the policy we wish to learn. And we are interested in learning the optimal policy. So we want to learn the greedy policy with respect to Q. So the target policy for us is the argmax over Q. And we define the behavior policy to be the epsilon greedy policy. So in this case, we are acting, in some cases, randomly with respect to our Q function. But you see how we are formally defining these two different policies, the one that we use to interact with the environment, and the one we actually care about learning. So by basically looking at the TD target in this case, so remember that in the previous slide, we basically said that in this formalism where we have a behavior policy and a target policy, the update, and specifically the TD target, essentially looks at the reward plus the discounted value Q function evaluated in the alternative action, ut plus 1 prime. So if we just take this same TD target, which is basically this term over here, and apply our definition of how we compute the alternative actions according to our target policy, we basically get, we only would modify this term inside the Q function, namely the argmax over our Q function. And by just doing some algebraic manipulations, we would basically get that this is equivalent to defining the TD target as the reward plus the discounted maximum Q value where the maximum is taken under the action U. Right? So here we're evaluating the Q value under the argmax, where the control is taken under the argmax over Q. And so this means that the overall value will be maximized, right? Because we're taking U in order to maximize Q. And so this is can just be rewritten as the max over Q. All of this to say is that by following this formalism, we basically redefine our TD target in this way over here. Meaning we're just replacing our TD target by defining it according to the alternative successor action. In this case, the alternative successor action is the argmax policy. And so this is what it leads to, essentially. Any questions here? Okay. And so basically now if you put this together into a working algorithm, you would basically get what is referred to as Q-learning, exactly. So again, we initialize our policy. We start our learning loop, whereby we are initialized at some state xt. We we basically choose a control UT in this state xt according to an epsilon greedy policy. This is our behavior policy, which we chose. And we observe the reward and the next state according to this control. Now we basically have all of our elements in order to define the update, which we derived in the previous slide, right? And so we can just repeat over time until we converge. Yes?
The behavior policy only generates the first, or sorry, one more sentence. Behavior policy only generates the first four, right? Okay, sorry, just.
Oh, yes, yes. So,
just to make.
Yeah. So in this case, we are using the behavior policy in our environment. Specifically, this generates the first four. And then we are kind of fictitiously assuming that we would take this action over here. Yeah.
Wait, sorry. Where does this new part? Where does this new part come from? What policy?
So here we're defining two different policies. One is a behavior policy which interacts with the environment, and one is a target policy which is the one we care about learning, essentially. So in this case, this ut+1 prime is sampled from this target policy. So here, this is in general terms. So we are arbitrarily talking about behavior policy mu and target policy pi. But specifically, when we look at Q-learning, the target policy is the greedy policy, so taking the argmax. And the behavior policy is the epsilon greedy policy. So we randomly act randomly epsilon % of the time. So putting this together, we indeed follow the epsilon greedy policy in our environment, but then in our updates, we are basically updating our Q functions towards the value of the successor action. Does this clarify? So there is some, of course, there's theory that have been developed for all of these algorithms, SARSA included. I thought it would have been nice to just mention the fact that it can be proven that under some regularity assumptions, Q-learning does indeed converge to the optimal action value function, and therefore that this process essentially leads to learning the optimal policy accordingly. Okay, so I think that basically these differences and these discussions that we're doing between behavior policies and target policies can be a little bit confusing at first. So let's try to build some intuition by looking at the difference in a simple environment between what we did before with SARSA and what we're doing right now with Q-learning. So let's look at this modified version of the grid world, whereby, again, we want to go from a start position to a goal position. No wind in this case, so no disturbance. But now we are assuming we have this basically failure region, which is the cliff over here, which is basically something extremely negative for our agent, right? So the reward here is, again, encoding minimal time, so -1 at all time steps. But if you do end up falling in the cliff, then then you're doomed. So -100 specifically, and with a specific choice of hyperparameters. So as a spoiler, if you wish, here we are comparing the policies that we would be converging to if we followed SARSA in blue or Q-learning in red. However, if you look at the kind of training dynamics over here, you would basically, again, here we're looking at, on the x-axis, the episodes, and on the y-axis, we're now looking at the sum of rewards that we accrue over episodes. And from here, you would actually say that SARSA is indeed performing better than Q-learning, right? So the catch here is that if you think back at our discussion on on-policy and off-policy algorithms, SARSA, being an on-policy algorithm, is essentially learning the best version of its kind of exploratory policy, if you wish, right? So SARSA, as we defined it, we were following this epsilon greedy policy. And so SARSA indeed converges to the optimal epsilon greedy policy. On the other hand, Q-learning, because we are kind of detaching our behavior from the target of learning, converges to the optimal policy pi star. So this is kind of, if you wish, kind of by induction, a property of one being on policy and one being off policy. Now, why would this explain this behavior over here? The reason is that in our environment, remember that both algorithms act epsilon greedily, right? So if you act according to the red policy and you're epsilon greedy, then sometimes you will actually be doing some random things and fall in the cliff, right? And so this is why Q-learning, when we kind of log over doing over training, we have a lower score. On the other hand, SARSA, because it, in order to account for this uncertainty of its epsilon greediness, kind of converged to the optimal epsilon greedy policy, which in this case is a safer one, that basically would travel more closer to the ceiling. Yeah?
Is it generally the case that SARSA will converge to a quote-unquote safer policy?
So I would say this is specific, of course, to this specific choice of hyperparameters and how we are discussing it. In general, of course, you can modify the algorithm of SARSA, for example, by having a decay schedule of your epsilon greediness, and then you can also converge to the optimal policy. So I mentioned theory for Q-learning, that this converges to the optimal policy. There's theory developed also for SARSA, in the fact that according to, indeed, some specific choice of your epsilon decay strategy, or more generally, some specific property of your randomness in your policy, and some conditions on your step size, SARSA also converges to the optimal policy. Yeah. Yeah.
But why does Q-learning achieve really converging and lower reward despite taking a shorter path? And why does both are not passing through the cliffs, so why does...
No, I think it's worth looking at this close and making sure we're all on the same page. So here, we're just visually depicting kind of the optimal kind of strategies that both algorithms converge to, right? So we learned some Q functions, and if we act greedily with respect to those Q functions, this is how the two algorithms would behave. Now, at training time, we're not acting greedily with respect to those Q functions, but we're acting epsilon greedily, right? So with some epsilon percent, we're doing some random action. If you consider the fact that Q-learning is actually going closer to the cliff, in some epsilon percent of the time, we would be landing in the cliff. And so this is giving it some negative reward during training. Right? So these logs are measuring the performance of the epsilon greedy application of the two Q functions that we're learning.
Is that reward -1 per step taken, or it's just the reward until you get to the goal?
You mean what is being tracked here?
That's the reward -1.
Yes, so here we are assuming that for every time step in our environment, whatever we do, it's -1 until we reach the goal. And then if we fall in the cliff, we get -100, and it terminates, and we spawned back to the start.
Okay, so even though during the training, the sum of the rewards in the episodes is lower for Q-learning because it's the cliff more often during those top policy explorations, the actual path that it converges to is, I guess, higher in reward than the blue path.
Yeah, this is very important. Does it make sense why? Yeah. These two paths are visualizing. Forget what happens during training. Training is done, and we converge to two different Q functions. This path is visualizing being greedy, so argmax, over those Q functions. And this is what you would do. Now, here what we're saying is, during training time, so before doing this visualization, what you would see is this, basically this plot over here. Why would you see this difference? It's because at training time, you're not acting greedily with respect to your Q function, but you're acting epsilon greedily. Oh, sorry, yeah.
Did you do the epsilon decay thing for that training?
No, so here is just fixed hyperparameters.
And if you did have that upgrade, would you like convert?
Yeah, so SARSA would converge to the optimal policy as well.
Okay.
Yeah. Okay. Any other questions on what we discussed so far before we move on to function approximation? Okay, great. So until now, we discussed algorithms that were basically deployed on these smaller scale, toy-like worlds, right? On the other hand, I'm sure kind of most of you, or some of you at least, might have heard about kind of the great successes of reinforcement learning, both in the realm of games. For example, AlphaGo and kind of the successes in Go are one of the peaks of the successes, at least with respect to games. But these are all environments where, if you think about the state space, these are incredibly large and incredibly high dimensional, right? So, for example, in the game of Go, you could have 10 to the power 170 different configurations of the board, which is, I think, more than the atoms in the universe or something like that. So this is an incredibly high number, right? And you could argue that games are actually among the easier things to solve compared to having things deployed in the real world, right? Where things that could happen are much more high dimensional even. And so the question is, how can we scale what we're saying with this model-free reinforcement learning approaches to these more high-dimensional systems? And the culprit here in scaling will essentially be to move away from our tabular expression of value functions. Again, remember that we are essentially, in everything that we did so far, we were assuming that the value functions or Q functions equally were essentially represented as lookup tables, right? So essentially, for each value of our state or state action pair, we will have a specific entry which represents the value of that state or state action pair. On the other hand, and this is of course problematic, as I'm sure you can imagine, for two main reasons. The first one is memory. So if you have 10 to the power 170 states, then even just storing this is an issue. But then, for the perspective of learning, there is a clear curse of dimensionality issue that comes up because to update values in our lookup tables, we have to visit those entries in the lookup tables. And so you can imagine how this becomes problematic. So this is where kind of value function approximation comes in play. And this is because, and basically where the main idea is that rather than defining these lookup tables, we want to define a parametric function with some parameters theta that basically approximates our values, right? So we will be moving from these tabular representations to something where the value function is basically a parametric function with parameters theta that in this case maps from states to a real value. And you can imagine something very similar for the Q function, right? Again, this is it's just a function that basically maps from states and controls to real values, right? So first of all, how does this idea address these two issues? First of all, we are compressing, or if you wish, amortizing the memory storage cost in storing only the parameters, right? So we're not storing one value for each state action pair, but we're only storing the values of our parameters. And also, in terms of addressing the curse of dimensionality, to some extent, we can hope that these value approximations can generalize across states and state action pairs, right? So far, even in our grid world examples, we were assuming that we had like a goal state, G, and that even very nearby states, if we wish to estimate the value of this nearby state to the goal, we would have to visit this state. On the other hand, you can probably hope that in the general case, as long as your representation of your environment is correct, this kind of knowing something about the goal state could also inform your estimate of the value close by the goal state. And so this is something that we can hope to have when we look at function approximation. Okay, how does function approximation look in practice for value functions? Here is where there could be many different ways of instantiating value functions through function approximation. At the high level, I think most implementations pick between one of these three representations. In general, we are assuming that we have a black box, that it basically represents our function approximation with some parameters theta. But in general, we could have these three main classes. The first one is if you're estimating state value functions V, it will be something that takes as input a state X, does some computation, and then spits out a value for the state. Similarly, a Q function could be something that takes as input a state and a control and spits out the specific Q function for the state and control pair. Or another interpretation of this second approach would be something that we still want to estimate the Q function, but now we take as input only the state, and rather than generating one output, we would be generating multiple outputs, one for each possible control in that state. Can you imagine why, I'm not saying this is better in general, but can you imagine why this might be desirable compared to the second one? Yeah.
I feel like if this provides set of inputs, then you could just include in your function kind of, or maybe even new set of inputs, then you could define the function in terms of you natively maybe? I don't know.
So I think your intuition is correct. Now, doing this for continuous action spaces is challenging, right? Depending on discretization, but I would not go for this when you have a continuous control space. But I think you're correct in the sense that this could lead to some simplification in how you represent Q, right? But can you, so assume both X and U are discrete in our case. Can you think of a reason why? Yeah.
Basically, you might want to have multiple value functions because just what, like if you were looking at driving a car somewhere, like distance in car versus cost of gas or something else.
I would argue probably not, no, at least at face value, because remember that we will be positing this as a learning problem, or as a regression problem, right? So either here you are assuming that you have different target Q functions that you're wanting to estimate, and then maybe indeed this could be helpful. But let's assume for now that we have a value function of one policy that we wish to estimate. But I think yours is a good intuition, but not what I was looking here right now. Yeah.
I mean, it sort of lets us probe in one specific state and then we can take the argmax over all of the Qs that output to get the output.
Yes, exactly. So I think these are all great points, but here I was more thinking about indeed kind of more of a computational aspect, if you wish. So remember that we are defining our policy generally, or at least the greedy policy, once we have learned the Q function, as an argmax over U. Now, say that we have, again, U is discrete, so we have a finite number of U's we want to iterate over. If we had now a function approximation for our Q function, this becomes an optimization problem, if you wish, right? So before it was just basically looking up in a table. Now it's an optimization problem. So if our Q function is something that, given a state only gives us the value of, given a state and a control gives us one value, we would have to do n queries where n could be very high. Right? On the other hand, if Q is an object that, given an x, gives us all the values of u, of Q x u for all u's, then this becomes, again, kind of a lookup in a finite number of elements, if that makes sense, with only one call. Again, I'm not saying this is the best way for going for it, but these are kind of insights behind these choices. And then not only is there, of course, flexibility in how you define these function approximations at the high level, but also within the black box, creativity is king here, right? So in some sense, you could go with something very simple, such as a linear model, or something very complex, such as an extremely deep neural network. But the high-level understanding remains the same. Okay, so I hope I have convinced you about the benefits of value functions or approximations. How do we instantiate what we've been saying so far in terms of Monte Carlo learning and TD learning when we have value functions, where we have parametric functions that represent our value functions. So remember that now what we want to do is essentially learn the parameters theta of our value functions approximators. That is, we want to minimize the error between the estimated value, for example, v theta of x. So the error, we want to minimize this error between v theta of x and the true value v pi of x. Seeing this from a regression perspective, this would mean potentially positing this objective function j, or cost function j, and we want to minimize the expected value of this error, right? So we want to minimize like the mean squared error, for example. How do we solve this? We have done this multiple times, for example, by taking gradient descent, right? So where we want to define essentially some delta, some displacement in our parameters of our function approximations, which goes in the direction of the negative gradient. Now, if we were to pick this choice of displacement delta t, what we will basically get doing some math is something such as we're basically taking one step where we choose some step size alpha in the direction of basically our negative gradient, multiplied by this error over here. Right? And I definitely suggest you to basically go through the derivation of how we go from here to here, but this is not very insightful. It's just basically applying gradient descent, stochastic gradient descent to this objective. But at the high level, it's important to basically fix in your mind that the form of our updates in our parameters is something that looks like this. Now, how we described it so far, it's kind of a chicken and egg problem, right? Because we're saying we want to minimize the error between our prediction and our true value function, but we don't have the true value function, right? And so in practice, what we do here is we basically leverage everything that we said so far in when we talked about TD targets and Monte Carlo targets, in order to define what is our target for regression, essentially. So similarly to how we did in tabular methods, we would have like a version of the Monte Carlo update, where now we are updating the parameters of our function in the direction of minimizing the prediction error, where this prediction error is between our prediction and the ground truth return, estimated as we were doing through Monte Carlo. And in TD learning, what we would get is the same thing, but now instead of pointing at the observed return, we're basically pointing at the TD target, right? Where we're using our estimate of future values as well. Okay, so what are we really saying here? So we are basically saying two different versions of a very similar intuition, right? So we said in the tabular dimension, where value functions are lookup tables, we were using interactions with our environment to estimate either our return, simply the sum of all the rewards that we saw, or a TD target, right? So the immediate return reward plus the estimate future value. In the tabular case, we were then simply using these two quantities to update individual entries in our lookup table according to our update equations. When we're looking at functional approximation, at the high level, we're doing exactly the same thing. But now, instead of updating entries in lookup tables, we're using those same quantities, the return, GT, and the TD target, to basically define input-output pairs for our regression problem. Right? And so this means that we will be able to define some updates to our parameters theta in a very similar way. Does this make sense? Any questions here? Yeah.
Like, if we do it iteratively, like our earlier example, we got decisions that we had and no one guess. Like, we got used to example.
Yes. So this is a great intuition because indeed, as you say, kind of the quality of my target evolves over time, the more this is getting better. And so you are actually pointing at, I would say, one of the key engineering breakthroughs, if you wish, that enable deep reinforcement learning to actually work in practice. Basically stabilizing learning exactly for this reason. And I think we'll mention it in a couple of slides. Yeah, but this is a great intuition. Okay, of course, again, here we mentioned everything in looking at state value functions, but everything holds exactly the same when we look at Q functions. So again, the kind of underlying regression problem that we would like to solve is basically minimizing the error between the predicted Q function and the ground truth Q function, which leads to defining a specific update in parameter space. We are, of course, not able to observe the ground truth Q function, and so we define the target of our regression either through Monte Carlo or TD learning. In this case, if we were to use a TD target, we would get what is referred to in literature as fitted Q iteration. And so, kind of, indeed, implementing this within our kind of generalized policy iteration scheme could look like something where at the policy evaluation stage, we basically approximate the Q function of our policy by using these update equations in parameter space that we just defined. Namely, we interact with the environment, collect some data, and fit that data, fit the Q function that better estimates those TD targets. And so this is what policy evaluation looks like for us. And then we use the updated Q function to basically define our epsilon greedy policy improvement step. Again, I hope that even through the repetition of very similar versions of those same algorithms, you're starting to see how different RL algorithms are all built around different instantiations of Monte Carlo learning and TD learning, and basically swapping or mixing different elements in those updates. But this would indeed be a working reinforcement learning algorithm with value function approximation. How does this look like in our reinforcement learning skeleton? Remember that last time we were starting to introduce this bird's eye view on basically all reinforcement learning algorithms out there, defined as a first stage where we generate samples, a second stage where we either fit a model of our dynamics or estimate some return, and use this to improve the policy. Indeed, if we look at fitted queue learning, which is what we just described, we would run the policy and observe our usual transitions. We would then use this data to define a target for our queue function regression problem, if you wish. Specifically here, we're using the TD target. And then use this to basically update our estimate of the queue function. And then we use the newly learned queue function to improve the policy according to an argmax policy improvement. Okay, any questions here? Okay, so then the last thing that I wanted to discuss today relates with basically taking these ideas, but now looking at kind of modern instantiations of these ideas, specifically in the field of like deep reinforcement learning, that is using deep neural networks within the same algorithms that we just discussed today. And one of the, I would say, groundbreaking results, I think this dates back to roughly 2014, is known as deep Q networks, or DQN for short. And we saw this, I think, a couple of times before. We saw these videos of these Atari games. But the point here is that, indeed, the goal where these algorithms were developed was solving, basically learn how to play optimally different versions of the Atari family of games. Specifically, kind of the interesting side of this is that we're basically using deep neural network, specifically at the time, convolutional neural networks, to learn how to control these games directly from images. And so this is where the power of, if you wish, deep learning and reinforcement learning was starting to be combined. And at a high level, kind of the architecture of these methods looked something like we have kind of raw images of our environment, which we are processing through multiple layers of convolutional neural networks. And then we are outputting here, at least in the original instantiation, one value for each of the possible actions that we could do in this state. So if you wish, the image for us is a proxy or observation of what the state X is. And so we have the state coming in the form of an image, and we have the Q value for all of the U's, all of our controls in this state. So if you remember from our 3 different categories of value function approximation, this would be the third one. So in some way, this work indeed used deep neural nets to represent our Q functions. And as we will see in the next slide, this introduced a number of tricks that basically helped to stabilize learning when we look at deep neural networks, exactly as your colleague was assuming before. Is this picture clear, more or less, what the algorithm is doing? Yeah. Okay, so let's look more specifically at these two these two solutions that were, I would say, extremely important for actually the success of these methods. And we're specifically talking about experience replay and what is known as using fixed Q targets. So indeed, these two ideas turned out to be extremely important to stabilize training because they basically addressed 2 main issues. The first one is that right now, if we're looking at function approximation of our Q functions, we basically have this inner loop, which is the basically regression of our Q function. Right? So as we explore in our environment, we basically are iteratively fitting the estimates of our Q function to the targets that we are observing. However, in this case, because we are active agents in our environment, kind of samples over time in our rollouts are highly correlated with each other. Right? And this is, of course, very bad from a perspective of regression and supervised learning, because we know that kind of statistical learning theory usually assumes that data is IID from a target distribution. And so the one big issue is that because we are now in an interactive engagement with our environment, the targets and the samples that we observe are highly correlated with each other. The second problem is indeed what your colleague was referring to, which is that the target that we are aiming towards to, that we are regressing towards to, is indeed a moving target. Because as we update the parameters theta, then the target of our regression also changes. And so this creates some problems in terms of stability. So let us look at how these two issues were solved in practice. So at a very high level, I would say the learning loop of DTUN goes as follows. So as usual, we are in a specific state xt, and we take an action ut according to the epsilon greedy policy. Again, the policy initially might be a randomly initialized neural net. As we are doing kind of classically in Q-learning, we store this transition of xt, ut, reward, and next state. And we store it in a replay memory calligraphic D. Now, so here's where the kind of the solution to the first problem actually comes in place, which is arguably very simple. But it's essentially saying that we know that the problem that we want to fix is that data and individual transitions are highly correlated between each other. So let's decorrelate transitions by storing them in a buffer. And then rather than using only the most immediate transitions, let us sample these individual transitions from that buffer. Assuming the buffer is large enough, then this would, the more the buffer grows, the more the individual transitions are decorrelated with each other, right? So what we're saying is that if we were to look at a single rollout, we would generally observe a situation where we have xt ut and the associated reward, and we have the next state xt plus 1, which gives us like the first transition. And so we could use this to make one update in our algorithm, right? But then as we move along in our episode, we would basically be observing some new transitions, which are highly correlated with the previous one, right? And so if we were to take these transitions online and sequentially, these would be highly correlated with each other. What we're saying, at least with this experience replay idea, is that rather than using these transitions directly, we observe them, store them in a buffer, which is something that it's just a large data set of transitions, right? Something that is a collection of these transitions. And xt plus 1. And by sampling from this buffer, we are basically decorrelating the transitions that we use to fit our networks. So again, very simple idea, but I think quite powerful in accomplishing what it was trying to do. Now, the second trick entails stabilizing this moving target issue that we were highlighting before, right? And the idea here is to basically leverage two copies of the same value function network. So instead of having a single network, Q theta, we are basically working with two different networks, Q theta and Q phi. So we have two copies of the parameters. The point in this solution is essentially that we will have one copy of the parameters that we are updating over time, and one copy that is basically a delayed version of that function that we're updating. So we start with some randomly initialized to the same thing policy, so two copies of the same initialized network. Now imagine that we have, this is like a time axis over training. We would have a phase where we are initially updating theta, and we're updating theta on fixed phi. And so over here, phi is actually fixed. Now, phi could be horribly bad at estimating the values at the beginning, but from the perspective of stability of the target, this is actually stable because it's consistent over time, right? Of course, over time, we will be kind of defining some regular cadence where we are basically updating the parameters phi to the potentially most recent version of theta, right? And so we repeat this. So then we have a new phase where we are updating theta, but now towards a slightly better version of the target network. Again, phi here remains fixed. And then we repeat over time. So you see that in general, we basically instantiate this delayed version of the same Q network, which stabilizes the target through this kind of delayed update. Of course, different versions of the algorithm vary in how this update is done. This is a very deterministic way of updating the target policy Q phi. It's been shown that this specific version is probably not the best choice because there could be a too harsh jump in updating the parameters of our target phi. So I would say probably right now the most popular version is referred to as Polyak averaging, where it's basically a moving average of the parameters. So if you wish, exact same intuitions apply, but the update of our target network Q phi is not done in a so kind of harsh, kind of step fashion way, but it's phi will be a moving average of previous versions of theta. But this is exactly the idea. And so you see that I would say these two contributions were basically key in making deep reinforcement learning algorithms work in practice. Does this make sense? Any questions here? Okay, so this concludes our discussion of value-based methods. Next week, we'll be discussing policy optimization-based methods, again, model-free, and then we'll move for our last lecture on model-based reinforcement learning methods. See you next week.